All right, so today what I'd like to talk about is non-relativistic gauge theories. So we've had lectures on non-relativistic theories with contact interactions, both for nucleons as well as for cold atoms. And what we haven't explored in any depth yet is what would happen if we had a non-relativistic system that had gauge interactions with a gauge field. So the prototypical example of this is what's called NRQCD, non-relativistic QCD. And so that's the example we're going to spend today on. And what type of systems would this be relevant for? Well, it's relevant for charmonium systems, CC bar bound states, bottomonium systems, BB bar bound states, as well as even top quarks when they come in pairs. You can also take the QED limit of NRQCD, and if you take the QED limit, then you get other systems as well, which I can include here, like positronium and hydrogen. We'll spend our time on the QCD systems, but the general framework that we're talking about would also apply to QED. So what is the power counting going to be in? In this gauge theory, the power counting will be in the relative velocity. So power counting in the relative velocity v, which we're going to assume is much less than 1. When we did the non-relativistic contact interactions, we used p. Using p or v, they're interchangeable, but it's very common to use v in the gauge theory, so that's what I'm going to do here. Another thing that we've already actually looked at in our cold atom lectures is that what happens with the Coulomb interaction. And a system is said to be Coulombic in the situation where alpha over v is of order 1. So that the Coulomb interaction is a relevant interaction. And that's actually what we're going to study today, is the Coulombic interaction being a relevant interaction. So what are the scales in this problem? So the scales are the mass of the particles. The masses are the same here in the charmonium system, but they don't have to be in the, for example, hydrogen system. They wouldn't be. And we're going to say that those masses are all generically of order some scale m, and we're going to call that the hard scale. It's the scale we're going to integrate out. The next scale in the problem that we need to deal with is the 3 momenta, p vector. And those are going to be of order m times v, the power counting parameter. And this is what's called the soft scale in NRQCD. And then the next scale that we have to deal with is the energies. And as we saw in our contact interaction relativistic theory, non-relativistic theories, these are smaller yet. These are order mv squared. And in the gauge theory, we call this the ultrasoft scale. Okay? And in addition, because this is QCD, there's also the scale lambda QCD, so we should include that in our list. I'm not going to say much about non-perturbative physics here. Generically, you have to decide whether lambda QCD is of order the E, is of order the P, and these are decisions that you have to make. I'm going to assume that it's less than or equal to the E, and basically not talk about the lambda QCD for this lecture. So this is the setup. This is the expansion that we want to do. But what are the relevant degrees of freedom? This effective theory is a little more complicated than some of the ones that we've dealt with so far. It actually has a fairly long list of degrees of freedom. So I'm just going to write the list down for you, and then we're going to talk about what the physics of the just different degrees of freedom in this list actually are. So let's say degrees of freedom. And we'll make a little table. We'll enumerate the degrees of freedom in the following way. We'll say, what are their energies? What are their 3 momenta? And then we'll say what fields are associated to those energies and momenta. And then what is their power counting? OK, so that'll be our table. And the first one we need is just the heavy particles. We have a CC bar, a BB bar. We have those heavy particles. We take the non-relativistic limit. Those become non-relativistic particles. And we're going to call them potential particles. So these are our heavy quarks. And the power counting that they have is exactly kind of how we outlined. This is sort of how we set up the power counting. So the energies are of order mv squared, and the momentum are of order mv. And the type of fields that we have are we have particle field psi, and separately we have an antiparticle field chi. These are no longer in the same field. They're separate fields. In order to make things simple for ourselves, we actually, in terms of how we define this chi, we sort of take the antiparticle part of the full relativistic psi, take the charge conjugation operator, and take the transpose. And the reason that we use that kind of version of the chi, a charge conjugation transpose version, is because that puts the psi and the chi on equal footing in the non-relativistic theory. We've already seen in our analysis of non-relativistic theories for the cold atoms and for the nucleons that the power counting was p to the 3/2, and that just becomes v to the 3/2 here. So I'll just write that in. Now, in addition, because this is a gauge theory, we now have gauge particles. And the gauge particles can interact with these potential fields. And the thing that's neat about NRQCD is that there's actually two types of gauge particles, both a soft, one that acts at the soft scale, and also one that acts at the ultrasoft scale. So that's going to be the additional things that we need in the table. So let's start with the soft. The soft gauge particle is an on-shell degree of freedom, so its energy and momentum are similar size. It's massless. These are massless modes, so they're massless quarks and gluons. And we have some fields associated to them. So let me call it A soft mu for the gauge particle, and I'll call the fermion phi soft, just to make sure that we distinguish it from our heavy particles. And if we go through the power counting for these guys in a similar way to what we did for the other case, this becomes of order v, and this one becomes of order v 3/2. All right, so then that's up to there. And then the next thing is ultrasoft, also massless. And in this case, we have mv squared, mv squared. We also need a gauge field associated to that, which I'll call AU, mu. And then we'll have light quarks associated to that, massless quarks, which I'll call phi mu. And these guys end up being v squared and v cubed when we go through the power counting from the kinetic term of these fields. So that's our complete list of degrees of freedom. It's a rather longer list than we've had in other effective field theories. And really, the heart of the matter here is that the physics of the ultrasoft and the soft sector are quite different. They have different power counting, and that's why we actually need distinct fields for them, even though it seems a little unnatural that we've divided up the gauge field into two different components. It's because physically these two different components are doing quite different things. The soft fields are actually responsible for binding effects, and the ultrasoft ones are responsible for radiation effects. So different physics. For S and U means different fields are needed. OK, so these are the fields. Now let's have a look at what the dynamics of the effective theory is. So one thing that we, of course, need is the propagator. And the propagator, as I said, for psi and chi is the same. And it's just a non-relativistic propagator, I over p0 minus p vector squared over 2m plus I0. So that's the same as what we had when we were doing contact interactions. Some things that are different are, for example, that there's hard physics that we've integrated out here. And there's different types of hard physics than in the contact interactions. In particular, there's gauge particles that are hard, where, for example, I could have a QQ bar annihilation to a gluon, and then a QQ bar production. And this particle here is hard and integrated out of the theory. And what that means is that this type of interaction becomes some kind of 4-quark operator in the NRQCD theory, like that. So that's part of the things that we're integrating out. What about the things that we're keeping? Well, one thing that we're definitely keeping is the Coulomb interaction. So let's talk about that for a few minutes. So if we have a Coulomb interaction, it's actually giving a Coulomb potential. And the way that one can think about it is that we have our heavy particles here. And then there's a potential in between them. And let me draw the potential with a different color. Let me use purple here for the potential. Maybe I'll make it a little thicker. And if we think about the scales here, if we are working in the center of mass frame, we have p and minus p. And then it scatters to p prime and minus p prime. And if we think about what type of scales are associated to the potential, it can exchange p minus p prime. So it has a momentum, which I'll call q vector, and that's of order mv. But if we ask about its energy, it can only exchange energy that's of order mv squared. Okay? And that means that it's actually off-shell. And therefore, we're not going to write down a field for that potential, for that exchange particle, which is a gluon, but it's not one of the gluons that's over here in our picture. Instead, the way that we treat these types of interactions is we actually just treat this as a momentum-dependent fermion operator. So the Feynman rule of this would be some coefficient, the potential that we have, and then some color structure. In this case, there's a T and a T bar, because the quark is in a triplet and the anti-quark is in a 3-bar representation. And this nu sub c is some coefficient, which in this case would just be 4 pi alpha s. OK? So that's what we would think about that. But really, you can think about this just like we thought about the interactions in our theory of contact interactions, except now the dot here is momentum dependent. So this dot has a momentum dependence, and I'll denote it by a circle like this with a C underneath when I mean those momentum dependent type interactions. OK, so that's a little different than what we had before, because now the dots are not just contact interactions, but they can actually have momentum dependence. OK, so that's one type of interaction, and that would be an interaction between potential particles. We could have contact interactions like this, or we could have momentum-dependent interactions like that. What other type of, how are these other particles interacting? So let's do some more examples. So the next example I want to talk about are what are called the soft fields. And these come in when we start thinking about this potential at higher orders. So if we think about the potential again, but now we think about the fact that the potential in QCD can have fluctuations itself, and in particular there are vacuum fluctuations of the potential, vacuum polarization. So we could have a potential which fluctuates into a pair of gluons, and those are soft. That's where the soft particles come in. The potential has momentum of order mv, and these particles have energy and momentum of order mv in these vacuum polarization type loops. So vacuum polarization dynamics is soft. And that's the sense in which the soft is associated to binding. OK? So what about the other types of fields? So that's why we need these soft gluons. What about the other one, which is the ultrasoft? So let's have one final example. It's ultrasoft. And in this case, it's associated to real radiation. So if I draw again, when we think about a Coulomb interaction, if I have a pair that's interacting like that, I can have a real radiation. And that real radiation will have the scaling of being ultrasoft. So you could say, well, why can't it be soft? Why does it have to be ultrasoft? And that's the reason it has to be ultrasoft is because the energy that the system has is only of order mv squared. So it can only radiate something of order mv squared energy into the final state. That's why it can't radiate soft particles. Soft particles can be virtual and exchanged like this, but they can't be real radiation like the ultrasoft. So the ultrasoft is what describes real radiation. This is the type of radiation that would, in hydrogen, make transitions between hydrogen energy levels. And that's what the ultrasoft fields are doing. And they have a different power counting than the soft fields. So as I said over here, we really need different fields to describe them. And that's kind of the dynamics of NRQCD in a nutshell. And we'll explore that further in the coming lectures.